So, okay, second class. Today we're gonna move from engineering. There was a lot of engineering in the first class. I heard that some were in physics were a bit overwhelmed. We're gonna shift slightly, at least, to image processing and images and working with images and how it's actually been used in human. But before we're gonna do that, we didn't show how we make images yet in MRI. So there will be at least one more bit of heavy kind of physics engineering intuition that we'll do. That will be creating images in the MRI, and then we'll move to the actual use. So before, okay, I forget about those things. I just want to remind you about what we said, kind of summarize what we said last week. Very basically, just the basic things. We said something about the fact that outside of the magnetic field, the summary of the spins doesn't create a magnetic vector, and when we put our subject or our proton in the water in the subject inside the magnetic field, we'll have this bulk magnetization, which we can summarize it as a vector which is oriented toward the magnetic field, and that's the vector that we're going to work with. That's the signal that we are working with when we're measuring. We said, wait, it was a movie once. That's strange. Let's kill the animation. It was working a minute ago. Okay, I'm gonna skip now. I was showing you this movie that doesn't work now. That was showing us how this vector is moving and process around the magnetic field. We showed that we can add excitation that will change the orientation of this vector, right? That was the B1. So we could play with this vector and create a graded transverse effect toward the XY direction. And then we also saw that's the last movie, which probably also doesn't work now for some reason. Oh, this one actually works. Yeah. So when we have this vector, we could have receivers and they could measure the signal, right? That was the thing we saw. So we have a way to measure this moving vector with receiver, and that's how we measure the signal. And then we identify relaxation mechanism. We say that there is excitation, and so we get the system out of its steady state situation, and then by excitation, and then we measure that. But while we are measuring, the signal is gone. We're losing signal, right? And this loss of signal was created by several phenomena, which we call relaxation, and we define at least two types of relaxation: the longitudinal relaxation, which essentially the vector is coming back to project toward the z direction, the main magnetic field, and was another relaxation, which we said which is faster. That was the T2, and that was the dephasing. The signal was lost because those protons, those spins, was losing coherence, getting out of phase, and so we lost the signal before it was fully relaxed in terms of the z direction.
Is that what we actually measure the transverse magnetization?
The projection toward the transverse plane.
So when you try to measure the recovery Do you have another coil that?
So I said that yesterday, and I have it in here. We said that we had different sequences, right? So we had the spin echo, which we said that after projecting the vector toward the xy plane, we can add 180, and then it will, so things will get out of phase, and then they will rephase, and that was the measure of T2 in the end. And I said that maybe it was quite fast. I said that with the inversion recovery sequence, which we had another 180. And then we can change the time between the first 180 to the spin echo sequence. And by that, we essentially, if we're changing this inversion time, we're getting the amount of vector, of organization vector that we had to play with is different, and that will be dependent on the T1. So by varying that one, there's other approach, but that's a classical approach to measure T1. By varying this Ti, the time of inversion, we've been able to measure. We are able to measure T1, and I think you did that already in the. You're going to do it today in the tier good.
And what do you need the third part for?
Say it again.
Inversion recovery.
So this one, the 180.
No, the third one.
That was the echo. So you remember there is the spin echo, the one that we have above, the 90 and then 180. That's just creating the echo. So we won't have signal to measure if we won't have this echo. So there is the 90. Thing is dephasing. We're echoing, and there is a moment in time we can measure again a signal.
But when you do the 90, don't you have the signal already?
Yes, and then it starts to dephase, and like I'm not measuring. My measurement is not perfect. It's taking time, and so on. So the 180 allow me to get another point in time in which I can measure a signal. If I wouldn't do it, it would be a free induction decay. I couldn't do inversion recovery on a gradient echo. Actually, the measuring is typically done on a spin echo.
Yeah,
do you remember gradient echo was just with a 90? That's the next thing I'm going to show in a second. But say it again. Ask again.
When you give the 90 up, and then you wait with and you give the 180, then the T2 comes into place.
So I'm getting a weighting of the. Actually, I have only loss of signal due to T2 and not due to T2 star. Actually, that's what happened.
Yeah, so if you want to measure T1, then.
But so if I would do it again and again and again, I will get exactly the same signal, right? But now I will do something else. I will also add another pulse in the beginning. I'm just going to move 180. So before this 90. So my vector is still projected toward the z direction. I'm flipping them, right? So it doesn't make a difference for our spin echo. We can still run the spin echo. But if I will do it in different time, because this vector that was projected, some of it will go back and so on, I would have the fracking that will be then projected to the 90 will be different. And it will be different according to the T1 effect. So that gives us a handle to measure the T1 component in the signal.
I think it's maybe I didn't understand the question, but I think you need the 180 because the 90 doesn't rephase, doesn't need progress.
But we could have done gradient. But yes, we need the rephasing to get an echo and which allow us to measure, right?
Wouldn't you want to know what the exact phase was?
Say it again.
Want to know what the phase is, like to get the actual phasing and not to rephase them, because then you won't get the signal. Maybe I'm not saying.
I'm not certain, but this echo will essentially give us a moment which we can measure some time later after this sequence of pulses, which is important for us.
When you're rephasing them, then you're changing the signal.
When I'm rephasing them, there will be a moment half of a TE afterwards, in which I can actually measure. There will be suddenly there will be a signal that I can actually grab. Okay. And I was also measuring the gradient echo sequence. We were saying that in general, if we were doing nothing, we're just doing 90, we'd get something which we call the free induction decay, right? Signal was falling, and it was pretty fast, and was affected by T2 star, which we said to ourselves T2 star is important because that's the thing we also measure in fMRI. Do you remember that? And then we said we can actually creating echo also in here by actually using gradients. So that's an additional small magnetic field on top of the main magnetic field, and it will be, if we will write in space, we're going to call it gradient. Okay, so a variation in the magnetic field in space, it's a gradient, and this thing will create even a greater signal loss, a strong dephasing, and if we will redo this gradient, rephase, essentially, just make the effect to the other direction, we're going to get an echo sometime in time after TE. Okay, so that was a gradient echo sequence.
And is that also, is that a T2 or
T2 star. So, and we said if we look at it from, if we fit a line between here and here, that will be exactly a T2 star. We can the exponent that explain the difference between the peaks will be a T2 star.
I just don't understand why it's better if they both give us a T2.
This one's just going to be lost, and we won't have a signal. In here, we're going to get a signal sometime. We're going to get an echo. We need this echo for the measurements. Okay.
So why would you use this one and not
The free induction decay, the what?
No, I mean the one that we can put the
Inversion.
yeah.
So see, this one was sensitive to T2 star. This one was sensitive to T1 and T2, and this one was only sensitive to T2. So we have, by playing with these pulses, we're getting different sensitivity to different relaxation mechanism, which all occur, right?
But why would you want the T2 star? Isn't it just artifact?
No. So, well, yes and no. We're going to talk about it in the end of this talk. T2 star is going to be important if we care about iron. It's artifact. Sometimes these artifacts are actually interesting. For instance, if there is a difference between oxy and deoxyhemoglobin, that's the Bold effect in fMRI. Or maybe I care about the amount of iron in the tissue. For instance, the basal ganglia, that goes very nice with in Parkinson, when basal ganglia is losing its abilities, it's also there is an increase in iron, and that's critical to know what is the amount of iron. And so if you want to get a measurement which is sensitive to iron, gradient echo or T2 star will be really crucial or useful. Okay?
Can you repeat how the 180 in the inversion recovery helps you see to 1?
Yes. So what we need to remember that we're going to change this inversion time. We're going to do this measurement several times with different inversion time. So this 180 flip the vector toward the minus z direction, right? And so you want to go back, right? So when we run this, the 90 and 180, this will affect only the one that still have a which are not cancelled. We can think about a moment, we flip them, and they go back. There is a moment there is nothing, right? Because they totally cancel. There is no vector. Going back, while going back, there is a moment there is no signal. For instance, I'm getting to that. That's called the null point. When the null point is the moment when the amount of the vector that is projecting toward minus z and z is just equalized, okay? While it's going up. So if I will run my experiments in the TI, which is in the null point, I will have nothing in here, and so I can do it in different times. I will get different signal, different projection, and that will be only a function of T1 in inversion time. So I'm going to flip inversion, change in inversion time, right? And I will fit in the exponent that will explain the T1 relaxation, because each time we get a different weight of the T1. Okay, I'm going to move on now. K-space. Okay, so this K-space thing, we want to get, so until now everything was kind of happening in a single voxel, we call it. We didn't have any information of space, okay? Now we're going to add information of space, and so we're going to get this T1 measurement, T2 measurement, T2 star measurement, or something which is sensitive to those measurements in space. Okay, until now we were in a single location. In MR we call it voxel, a pixel in volume. Okay, instead of pixel, voxel, or volume. Now I want to measure it everywhere. Okay, that's the strength of MRI. That's why we want MRI, right? It's so nice in humans. We can measure them without opening their skull and so on. So that's the idea. And we typically when we do the measurement, and that's the painful part, we measure it in Fourier space, okay? So I'm going to say it many times, but this image can be also represented as a weighted sums of different frequencies in space, right? So we can, anyone who was here in CS maybe, like so the idea that we can take different waveforms, I'm going to show it many times. So, but we can create an image by combining different images which have different frequencies, right? But, okay, there will be a slide that will do exactly that. So I'm going to skip it for now. We'll see it first in the 1D, and then we're going to move to 2D, and you should project what you understand in 2D to 3D, because sometimes that's actually done in 3D, not only in image but in volume. Okay. So let's now stay with this 1D example. We have two beakers with water, okay? And I put them inside the magnetic field, and I'm measuring from them. And because there is no difference in the magnetic field, okay? They all have the same omega. They all have the same frequency, right? And when I measure from them, I'm going to get a signal, right? And this signal not going to tell me anything about where it's coming from. It could come from this one or from this one. It probably just came from the sum of both, right? I have no information about space. Now I can do the same experiment, but create some perturbation or gradient in the magnetic field. Okay. So now each one would have what? A different what? Slightly different Larmor frequency, right? Because the Larmor frequency was a function of the magnetic field, and they experienced a slightly different one. Okay, so now if I'm going to sum one which has one specific frequency and another one which have a different frequency, right? I'm going to get the sum of both. And just to remind you, we have a way to create this variation in space. We call them gradients. Remember I mentioned those. Part of our machine have gradients. Okay, so that's something we can do. We can create this variation in space. So if I'm going to sum them, I'm going to get something like that, right? Okay. So now I have a time series with two frequencies. And so I can write the equation that describe the location and the magnetization that each of them will create as function of the gradient. Just remember that we can describe this time series. But what else we can do? What these kind of things kind of like suggest we might be able to. And I already said that in the beginning. Fourier, you learned Fourier, right? You learned Fourier in last quarter. Okay, so we can do Fourier. We can do Fourier analysis. And just to remind what is Fourier, I know you all learned that, but we can talk about we can take this oscillating curves, right? Or create them by changing the amplitude, the frequency, and the phase, right? And so that's one thing, and then we can describe any time series by a weighted sum of those. Okay. So I can say that this time series is a weighted sum of those three, and I can put a weight on each of them. Right? What is the A? What is the how much I needed from each of them? Right? What is the weight? And so I have a description here in the Fourier space of how much I need. What is the fraction of each of them to create this time series? That's okay. Yeah. Okay. So then I can say that this time series have two peaks in the frequency space. That's fine. Okay. So we see the logic here that maybe if we would have a gradient in space, we will be able to encode the signal for different positions, right? Now, if we will talk about it in image space, in 2D space, instead of talking just on frequencies in space, and I'm going to talk about frequencies not in time or in one dimension, in 2 dimension, right? So now I have like, so there is the frequency of in X, right? It could be this frequency or half a frequency. So it's how many repeats we have in this wave, right? You see that this one is double of this one, and I can have it in the other orientation, or I can have some kind of like combination of them, right? And we can combine them again, and so as we combined before to get a time series, we can combine them again and create an image. Okay? That's fine?
And for the pulses, do you also vary the energy of the pulse needs to be different for different magnetization? So do you also vary it, or you just use the pulse that's combined?
We see that. We do. We have gradients in X, Y, and Z, and we can create any combination of those according to the strength. That's what you're asking.
Like for the pulses, for the 90 and 180?
No, those one are not, but there will be additional one which will create gradients. Other pulses which will create the gradient in space.
I don't understand what we're looking at, like frequency or amplitude, or like wave plot.
In here, I just showed you different frequencies, but special frequencies, right? And I just said that we can sum them, and I didn't say in what weight, but we can sum them and we can give them with different weights, and that would create a different summation result, right?
What orientation representing the signal? The orientation of the. I mean, what would change the orientation? I mean, the signal itself. With doctors,
Leave that for now. I'm just talking about some waveform in space, and they could have orientation. I can, right? It's just a combination of some waveform in X and in Y, and so in here it's this sinus and cosine, and I get some kind of orientation in space.
So the signal is the current that you measure with the coil, and this is what you keep this is what you.
Wait, don't run to the MR interpretation of that. I just did one move here. I just said that as we can speak about frequencies, we can also talk about this waveform in space. Just that. And so, before we talked about an image, we can think about of the image as a weighted sum of many waveform like those, right? And so these weights have some kind of we can combine them, right? We can combine them and put them in different amounts, the different weight, and we're gonna get an image. Okay? So you can always move from an image to its representation in this Fourier space. And that's not an MR at all. That's like JPEG and things like that, right? We can think about the high frequency we see, the low frequency we want to save in an image, right? That's actually a big thing for anyone who work with images. What frequency we need to reconstruct an image? So how much information we need? What can we remove from our? It depends what we try to do to measure it or to save it and so on. So this analogy of image in image space or in Fourier space is just a transformation between spaces, which that's the only thing I want you to know for now, for this moment. And so just to give you another more sense, like more intuition about that, we can talk about high frequencies. So if I'm only keeping the high frequency and do the transformation, I will see the high frequencies, or maybe I remove the high frequencies, I will see only the low frequencies in this image.
How do you represent space?
I'm not in here, and let's work only with the magnitude for now. You're right.
So these pictures are no phase.
Yeah. For the sake of what we're talking right now. Yeah. Let's work only with the. Let's not talk about the phase for now. But there is another. We need also another one for phase, right? Is that okay? High frequencies, low frequencies that capture different something about the image, right? I guess you can see the brain in both, but in different way, right?
I mean, why this one is the, I think I couldn't see the detail.
In this one?
Yeah, this one is the high frequency one.
Sorry, the low frequencies. So low frequencies. I said it. Correct me. Yes. So this is the low frequencies. I'm sorry.
Okay.
This is the high frequencies. Removing the low frequencies. Around the mean. The mean is like. Okay. Sorry. Okay. So we saw that already, and just want to tell you that those gradients we can play with them. So the strength of those gradients. So as we have, as the strength is greater, we'll be able maybe to encode more information in space, right? We will have bigger gradients. So we can say that, and it's a linear thing. So we can talk about the strength of the gradient and what kind of the strength of the gradient field that we created, and we can talk about what gradient actually creates in space. Okay, so that was amplitude. Here it's magnetic field change, and if it will be stronger, we're going to get a stronger variation in space. Not really important for us now, but that will be important in the way we want. Actually, not important for us so much. We're not going to get to this level. What I want to say here is just kind of summarize. So the gradient allows us to create some kind of a variation in the Lamont frequencies in space. It's always some effect that we always adding on the main effect that's coming from the B0, okay? And they have units, typically in units of millitesla per meter. So that's the units. And so the first thing we might, okay, so now we need to encode. We have 3 dimensions in our image. It's a volume, right? We define it as typically we can think about a slice, some location in the brain, right? Our brain problem is a 3-dimension problem. You see that, right? It's a volume. So I'm gonna first move it to a 2-dimension problem, and then we're gonna talk about the 2-dimension problem encoding. But it's gonna be more of the same. Kind of. This is slightly different. The first one, which is a slice selective pulse, what we first create a gradient, okay, and then we're going to excite only on this one. So we create a gradient. And now we're gonna excite only in the right frequency. I'm saying things which are now in a perfect world. We're never exactly doing that, but we're going to try to excite in the very specific frequency that we want, that is related to this position in space. And so instead of getting signal from everywhere, we're going to get it only from this slice. So just by that, I move my problem from a 3D problem to a 2D problem. Okay.
How do you know the frequency related to?
So I know what is magnetic field strength. I know what is the Lamont frequency. I can actually measure it, and then I know that my gradients are linear. I know how long I turn them on, and so that gives me how they will vary in space. What is the variation that I'm going to get in space? So according to that, I'm going to say, okay, this is Lamont frequency plus some epsilons plus some energy, and so if I'm exciting in here, I'm going to get this specific size, roughly.
You change it to a 2D problem, but the problem is now in the YZ plane. So, it's whatever. Z to Z included. So are you allowed to have gradients on the Z axis?
Yes.
Okay. But otherwise you won't be able to.
No. Okay, but all the spin in this slice for now that I have in here is going to contribute to my signal. So it's still a big problem, right? I have like many locations, and all of them will contribute to my signal. I still need to do something, but let's first. Didn't meant to do that. Wait.
Why is it
The time for break? What is that?
Maybe I can ask a question.
One sec. Here we are. I'm going to do that, and then you're going to ask a question. Just turn a gradient, there is a specific frequency that I actually. Okay, so we have a gradient, so that means my RF frequency will work only on one location, and so I'm getting the signal only from there. Just very simple metaphor here. Yes.
Starting to have slides ago, what limits the strength of the gradient?
SAR. I mean,
Or
the biggest. Well, it actually depends on the how they've been built. So what kind of you remember the magnetic field is a function of the electrical current that we have. So it actually has something to do with the design, the actual design in space of these coils. So manufacturers will try to do them stronger and stronger to be able to maybe to get a. But the main effect is that it's either if you're gonna turn it on and off very fast, that's one option. You can actually do it long, which you make your scan very long, and you're gonna get very nice resolution. Or you can turn on and off very fast, but to very high amplitude, and that might create SAR effect. So warming the tissue, which we also not allowed. So that's the limitation.
Is it important that all the things are producing the signal?
At the slice. Everything in this slice have the same Larmor frequency. I am excited in this Larmor
Only
frequency.
the ones who are affected.
Yes, but it's very still many, right? All everywhere in the slice. Just if I actually want to get an image, I need to do more. That's not enough, right? I move from the full plane to the slice, but I need still from the slice. I need to now location in the slice. So I still have to have a long way to go to get a signal per location. Okay, so there is now within the slice we can turn other gradients, or we can turn the other two gradients that we have, and as we turn them, the spins will try to start to acquire phase. If you want to, they will move in a different rate, in a different frequency, and so in time they will acquire a different phase, right? I can do it both in X and in Y. So this one is in Y, the other one is in X. I can do it in both. So now I have a signal which is dependent on the slice I select, and also by the gradient that the strength, their location, the strength of the gradient I turn on, which there was other two, and where they were according to this thing that's created, like in each position in time, this one all of those have the same phase, right? But they're different from their neighbors, and I could say the same for these ones, right? So now I have kind of like a big problem that I need to solve, but it's solvable because I know the gradients, I can measure the signal, and that's a problem we can solve. So again, the Z direction allows the first we can do the slice selection, and then so now with the slice selection, all the signals have the same information, all those spins in the slice give us the same signal. Let's say we turn one of them, that will allow us to separate between anyone in this line versus everyone in this line, right? Because they're getting a different phase in time, right? And I can turn another gradient that will also dephase them in this direction, and that would give me location, in theory.
So the gradients are simultaneous.
Yes, could be. Yes. Typically, we turn one for a long time and one for very short time, just to create. We're getting out of phase and then creating another phase, which they aggregate in time, given that they already went out of phase in one of them. But yes, you can do whatever manipulation you want.
The X and Y gradients are turned on only after the pulse?
Yes. In this kind of 2D imaging, there is a 3D imaging, which actually I'm not sure about. But my guess is that not in the other one.
Why is it important that it would be up?
Because if not, then when we excite, they actually each of them have a different. They don't have the same Larmor frequency. I cannot. Right. Just clear things up. Right. First select a slice, and then we have this 2D problem that we need to solve.
yeah, it's not so clear, like the relation between the gradients and the pulses, because the measuring is within the pulses, like within the sequences.
Say it again?
The measuring, from what I understand, is a part of the sequence. Of the measuring, the sequence has
This
some
90 that I gave, for instance,
Yeah.
I will give a 90 that will translate a specific set of protons with a specific Larmor frequency. So giving that there is
But isn't that built on the gradient?
say it again. I don't.
Sequence.
So there are different gradients in here, right? One of them allows us to excite with a 90, for instance, only a specific set of protons that are in specific Larmor frequency. Then there will be others that will then allow us to encode the location in space within this slice, between those that were excited. I will show you how. I didn't explain exactly how. We can actually measure it very long at time. I think in the Tergul you say that you can measure in time and then solve the Fourier, but we typically don't do it because it just will take very long. Okay.
How can you know that, what do you define as a slice?
What I define as a slice.
How can you control this? You apply this gradient.
Right.
And you apply the full. So how do you know exactly?
So that's what I said, that things are, like I would try to describe everything as perfect, like there is a really, decrement frequencies in space and not continuum, and like I can actually excite in a very specific frequency and not in some range. And so yes, all of those things will create imperfections. And the fact that these things are, even if when I'm doing that it's not square, I'm not going to get into that. But so yes, there's many imperfections, but still working good enough, but not perfect for sure. Okay, so actually we're not measuring, we're not acquiring this signal in time. What we try to then do the inverse or doing the Fourier. What we are doing is we try to fill K-space immediately, just to say what is the weight that we're having. So this thing is like, the intuition for that is always hard. And besides the people actually doing it in a daily basis, most of the people who even understanding that, forgetting that each time I need to teach themselves it again and again. Okay, so just for me at least, that's the case for me. I need to okay, I understand that. I know that I can understand it, and then I forget. So what I'm suggesting here is maybe you will try to get. I hope you will have some intuition about how it works. I'm not gonna get you to the level that you can go and reconstruct the image tomorrow. Given that I will give you a raw data, it will be hard to just create an image. And most of the users, most of them, never doing it. There is, where is the user getting the MRI already as images? But it's good to know at least how it's been done, at least once. Get some intuition about that. Unless you're working on K-space reconstruction, there are people like that. For instance, there is the ENU day, so that's the meeting day for the neuroimaging unit, and there will be a speaker. His name is Mickey Lustig. He's an amazing speaker, and that's the problem he's facing. He tried to make things. He tried to reconstruct the image as fast as he can, having as little data as he can. So if you want to hear from the super professional, also the most cutting edge, his research is really cutting edge in the way in the algorithm he's using in order to reconstruct images in the fastest way, and so on. It will be interesting. I think it will be interesting for you to go and hear that from him. So you have the opportunity to come. I think in a month or less months. I will let you know when it's happening. There was. So he's the last speaker. He's an amazing speaker as well. Sorry. Okay. So I'm just reminding you that we want to fill K-space. If we would have K-space, we'll have the image. Just that, right? So let's try to think about a way to do that. And I'm going to move for 1D problem to try to create this intuition for you. So let's think about a uniform something in the scanner. Okay? And so and then I'm going to start with spins which have no phase, so they all align, and so the signal I'm going to measure is going to be summed across them, and going to have some signal. Okay. I'm going to sum them, right? Just going to, let's say my measure signal is going to be going to reflect the summation of all those spins. And then what will happen if I will start to create a phase to those spins? So remember, we can create phases, right? So what would happen now to my signal? You remember our gradient? They create phase to those spins. So now, let's think about only that for a second. What will happen? It would sum to 0, so it will be cancelled. Okay. And I want to argue that have to do with the frequency in space of this object. Okay, that's important. That's a key point for me, because if I would have something which have a different frequency in space, what would happen then? Things will be cancelled.
Depending on the
That's true. Depending of the frequency of this thing this helix in space, and the frequency of my object, there will be times in which I will actually see a signal which will reflect the frequency of this object. Okay? That was clear? That is if you understand that, you understand it. We said that in here, the signal will be cancelled, right? Because all the spins are going to cancel each other. In here, they won't. If the frequency, or the special frequency of these spin vectors, the summation of them, and the frequency of the object are similar, then there won't be cancellation, because in here there is nothing that will drive a signal, right? Only in here.
I don't understand what the object is.
Something. I just put if you want, I put I create a very big box, and I put like air, water, air, water, air, water. There's many reasons why that won't work in MR. That's for the game here. Airborne, air. Okay, some water, bony tissue, watery tissue, bony tissue, water. Okay. So now this area in here doesn't add spins, right? But in this case, there's nothing. So only those adding to the summation of those spins, right, in space. And in the right frequency, we get a measured signal, right? So not like in this case. In this case, we're going to get a signal with this vector of spins in space. Is that clear? Yeah? Some kind of intuition? Please? Yeah?
It needs to be just exactly what's the ratio between the frequency of the helix and the object?
We're going to get the maximum signal when they're exactly the same. After that, it's going to be a weighted sum. Right? So there might be other cases which they won't cancel totally. We're going to get the strongest effect when they're exactly with the right waveform. Okay. So with that, I'm getting back to our gradients. We just said that as we turn the gradients, as function of time, we're gonna add phase, and it will gonna be linear, right? So we have here a gradient, and in some point in time, we start to create phases, right? Because each of them have a different Larmor frequency. So when we add them up, some were faster than the others, right? And it looked like a phase in space. And if I'm going to turn the gradient for a longer time, I'm going to get a different frequency. Okay? It's going to be like that. Maybe, yes, it's going to be like that. So in a longer time, we're going to get a different frequency in space. Okay? So and we actually understand it fully. We understand that the phase that we accumulate is function of the gradient, that's G of T, some constant of the magnetic field, or position, that's Y, and time. Fine? Simple.
Do all tissues accumulate space the same pattern?
Say it again?
Do different tissues accumulate space?
Yeah, this is only about position. Yes. Yes. Let's say yes for now. Yes. Yes. For these gradients, yes. Yes, because we only look. You should think that you only look on the water protons anyway, which have only one Raman frequency. So yes. Time. Like one more slide. That will be exactly the time to shift. Okay. All my lambda were gone, but there was a lambda here. Funny. I just want to say that we can define this lambda as the wavelength of this helix, and we can just call. I'm just going to give it a name. I'm going to call it K. So this parameter there of the accumulation of phase, I'm going to call it K, and everything beside the location. Okay. Just combine constant in a particular time. And so, and I can show, and I'm not going to show you now, that we can say that it's just 2 pi divided by lambda, sorry. And so what happened here now, when I'm measuring a signal in time, I can also describe it as a function of k. Okay, I'll just change this thing to k. So now I have a signal as function of k. So now each time point give me a weight on a specific k. Okay? Maybe. So at least you have some kind of intuition of that, right? Because you remember we changed the lambda, we get different weight of different frequency in space, and that's what I'm saying in here. So in each time we're measuring, we're getting we essentially getting a measurement of a specific frequency, spatial frequency. And so that's how we accumulate a signal in K space.
So one excitation gives you all the frequencies?
Yeah, we're gonna see that. It depends on the way we're running it within K space. In the simple version, it will give us a line in K space. And there will be ways maybe to run between lines in K space. I'm going to show it in a second. Okay, so here it is. We have the 90. After the 90, we turn the XY gradients with some strength, so it takes us to some location. Right? We can do the 180. It will take us to the opposite position in K space. And then I'm going to turn on here the gradients, the X gradients. And that will, as I'm waiting in time, I'm going to acquire the weights of these lines of this line in K space. And what people in many times do, they don't want to do line by line in K space because that takes very long. That can take like about 20 minutes per slide, something like terrible like that. There is no subject that actually want to do that. So instead of doing that, what we can do is try to write like sequences which will move us within K space. So now we're gonna want to jump between lines and get some kind of sampling of K space. So that's the intuition in here. Get us to some position, and then we can turn it off and get to essentially a different location in K space. I know that's a bit above your head. Like, I don't expect that you will. Okay, now let's write it for ourselves now. I just want you to get some kind of intuition of this EPI thing, which is this accelerate rate to measure K space fast. So it's okay if you don't get it fully, but what I want you to know is that this type of acceleration is thing that we always do in MRI. So in any fMRI work, we'll use this EPI. So when you see EPI, you know they did some kind of a fancy. I will show you to. They will do some kind of a fancy turning off, turning on of gradient in order to measure K-space really fast, but doing that they also reduce their resolution. They might have more artifacts and so on, but at least they get some kind of a hold of the full image because they changed something in here. Now they moved line in K-space and so on. Okay, and that's how they will. That gives us a fast way to sample the full K-space here. Pretty fast. You didn't understand that. So before we were in a specific position in K, and we turn the gradient on, and as we wait with time, we kind of acquire the full line in K-space. And now we need to do it again. Move ourselves to another location in K-space, excitation, measure the full line in K-space. Move to the...
What's the difference between this and the other, slower one?
The fact that you can do all K-space in one excitation. Just running through K-space by turning on and off the gradients, and that give you get the same amount of measurement. That means that you probably would have a lower resolution, right? Or you might have artifacts. We're going to see why you might have an artifact, or maybe we're going to see. But at least you got the full brain or the full part of K-space that you want to measure in one excitation.
How does turning on and off the gradient help?
Shifting inside K-space.
Not sure.
Let's do that again. This thing, we said that a specific X and Y will take us to a specific location in K-space, right? With some kind of winding in X and some kind of winding in Y get us to a location in K-space, right? And as I turn it now on for a longer time, I'm going to measure a specific location in K-space, a specific line in K-space. Now, if I'm going to change the X and Y, I'm just going to start to jump here.
To identify the same gradient, right? Different.
The same gradient, but for different durations.
Okay. So we're going to have this number of slices. Every slice I chose will have its own K-space into these.
Yes. Now, some people like this working in the Fourier space or in the K-space. So they design different ways to sample K-space. So there are people who will like, that's the work, that's the research, they will say it might be better to do it line by line. Maybe we do this ecoplanar that allows to jump between line K-space. Maybe we're going to do spirals and so on. I mean, we can write the equation, which we didn't, that will allow us to do this manipulation in K-space. And then sample, and this sampling scheme will get us more or less information. For instance, this one will get us many times the mean. This radial, this one will create one kind of artifact. This one will get us a different kind of artifact, and so on. And that's important. Ghosting versus blurring, and so on. I know. I need to finish 2 more slides because I just don't want to continue K-space in the next class. I want to be done. Yeah. Just remember that whenever we measure, so if we take a smaller part of K-space, we're gonna get blurriness. Okay. If we're gonna take different samples within K-space, but not in just take every other line or something like that, we're gonna get folding. That's what we have in here. And maybe you're playing with that a little bit in the table about aliasing. Okay. And actually, this folding is a huge problem, but it's also a great advantage for people who try to do acceleration. So there is many interesting things with that. I'm just going to say that, I'm going to run through, but there are ways to try to accelerate because there is symmetry within this K-space, so sometimes you can only take part of it. Or maybe you take images which have aliasing, but you're measuring with different coils, and that allows you to then try to unpack this problem. So there is a lot of work on ways to try to accelerate the measurement by control the aliasing or control the problem, and then using and then try to unpack the aliasing. Okay, so that's all those things called parallel imaging, and they allow acceleration, allowing us a faster measurement. Aliasing, this is like just the image turn on itself. So it means that you don't have enough frequency to describe the full frequencies that exist in the image. Okay. You don't need. For me, I just want you to understand that, given that we're working in K-space, there are people who, and we didn't explain, right? We need a full class for that. There is a full work in engineering. We try to accelerate this problem, making the measurements faster. That's the only thing to know here. Okay, and that will allow us now to move to quantitative imaging and imaging and brains in general. Break. And we'll continue in 1:05. 10 minutes. אבל העליתי אותה, ב-PDF לפחות. אבל אני... באמת, שמתי אותה היום. אם לא, אולי שמתי אותה במקום אחר.
קבועי זמן שונים שיש יש בעצם הספיקה על K זה בעצם לפי הזמן, ככל שהעוצמה של השדות הם מונחים קבועות, לא משחקים איתה. אבל ככל שהעוצמה, ככל שזה תלול יותר, אז זה יהיה יותר מהיר הספיקה על K, אבל אתה רוצה באיזשהו מובן
תן לך יותר רזולוציה.
תן לך...
תעבור יותר מהר בנפוק השני.
כן, אבל מצד שני אתה רוצה גם שהלמור פרקוונטי יהיה הרבה יותר מהיר מכמה שאתה, מהמהירות שבה אתה עובר על שאתה סורק תדרים.
אם אני סורק תדרים, אני מסתכל מה אני בעצם סורק תדרים, נכון?
כן.
אם אין עוד בהבדל בין התדרים, הרזולוציה שלי במצב היא כזאת שתאפשר לי שם לי בעצם קאפ על ה-higher frequency שיש לי.
כן, אבל אתה רוצה גם שהלמור פרקוונטי עצמו, כאילו שהמהירות שזה מסתובב, כי אתה רוצה לקבל הרבה תדרים, כאילו עבור תדר ספציפי, אתה רוצה לקבל ממש.
מז'מנט אתה מקבל? זה די אבל כל נקודה בזמן נותן לך ה-weight של הקייס. כמה היו בתדר הזה, כמה היו בתדר הזה, כמה היו בתדר הזה. כל נקודה בזמן אמר לי בסוף נקודה בקייס.
בסופו של דבר, איפה אתה רואה את הדעיכה?
אבל נכון שאם נצחה התאמנתי פה מהדעיכה, אבל תדרים שאנחנו מודדים אחרונים הם פחות סיגנל רק בגלל דעיכה, אז זה רוכב לו דעיכה. פה עכשיו דיברתי על העולם כאילו אין לו דעיכות. אני רק עושה להם ויינדינג והם לא דועכים בגלל נסיבות של טיטו וטיטו סטאר וכל הסיבות האחרות. וזהו, כל האפקטים אחרים.
אתה מכניס את כל הטיטו וטיטו סטאר,
זה נכון
שזה יקרה הרבה יותר מהר ממה ש...
זה קורה הרבה יותר, אנחנו מדברים פה במיליסקנד.
הטיטו סטאר אמור לקרות יותר מהר, או ההפך.
לא, אם טיטו סטאר רואים לנו את הסיגנל, זה נכון שאם אנחנו לא עושים איזושהי פעולה, נגיד ספין אקו, מחזירים אותם ב-180, אנחנו נקבל, אם נתחיל להעלם לנו את הפרקוונסיז האחרונים שמדדנו, שאספנו, הם כבר כמעט בלי סיגנל, הם כבר עברו פול דיפייזינג, אז נורא קשה למדוד שם, אין לנו הרבה שנה. זה נכון מה שאתה אומר.
כל התמונה הזאת אתה מקבל מהר, כאילו אתה מקבל תמונה שלמה כזאת, ואז אתה עושה ספין אקו ומקבל עוד תמונות כאלה, והרבה תמונות כאלה, ומהן אתה מוציא.
אין לי ספין אקו, אני עשיתי שם את ה-180, ואז יש רגע שהם הגיעו לאקו, נכון?
כן.
חוץ מזה יש להם גם דיפייזינג, אז זה נשאר גם דיפייזינג, האפקט הוא רק של טיטו עכשיו. הם יצאו בפאזה, גם 90, התחילו, ואז יצא להם 180 כי אז הם יעשו ריפייזינג. אז זה אני מוסיף, על הריפייזינג שלהם, אני מוסיף גם שינוי מרחבי או משקול של התדרים המרחביים. עכשיו, זה נכון שאם אני, תדע זה נמדוד אחרון, יש בו, בספין אקו זה תלוי כמה הוא קרוב לאקו, בסדר? אלה שהם הכי קרובים לאקו יש להם מקסימום סיגנל. בגרדיאנט אקו, על האחרונים יש פחות סיגנל כי הם עברו דיפייזינג. ולכן איך שנחליט לרוץ בתוך K-Space, קבע לנו את אלה שנעצוף ראשונים ב-K-Space. המיקום שלך בזמן שנאספת בתלות בסיגמה שהרס לגן אקרוסטנק, או ישנה את כמה סיגנלים ממך. כאילו כמה... SNR משפיע על היכולת שלנו יותר תמונה, וכאילו אתה טועה, זה בטעות. ובגאנט אקו באמת התדרים האחרונים, הכי קשה למדוד אותם. שווה לפייזינג, יש אנשים שעושים את זה, משנים את ה...
אבל בעיקרון מניחים לשיטה הזאת כביכול עובד, שמניח שאתה תופס את הדעיכה בנקודה אחת בזמן. זה לא משתנה, ואתה לא צריך לראות את השינוי. ובעצם אין פה שום מדידה של T2 או T1.
אז זה רוכב, יש רק אפקט, זה נכון שבין...
כאילו, זה היה השיטה הזאת שעובדת גם אם לא הייתה דעיכה בכלל.
אני מוצא ערכים בקייס ספייס שהם מגיעים מכל הווקסלים. אז יכול להיות שיש סירקמשיב שאני, כיוון שהייתה פה גם דעיכה בזמן, כלומר סימן דעך בזמן, זה מגיע מכל הווקסלים, כן, שמדדתי נגיד. אבל יכול להיות שיש תדרים מסוימים בקייס ספייס שאני מדוד אותם עם יותר סיגנל ויש כאלה עם פחות סיגנל. זה לא מקום מסוים, אבל זה תדרים מסוימים שיש לי לדעים יותר סיגנל ופחות סיגנל. זה דעיכה. בסדר? בגלל שאני מודד בקייס ספייס, אני מודד כל הווקסלים במכה, את התדרים המסוימים שקשורים לכל הווקסלים באותו תדר. בסדר? אתה זוכר שהאינטראקציה יכולה להגיד ללוב, תדרים נמוכים ותדרים גבוהים, בשביל את המשחק הזה?
כן.
הורדתי את התדרים הגבוהים, זה השפיע על כל הווקסלים, הורדתי את התדרים נמוכים, זה השפיע על כל הווקסלים. בסדר? זה לא מתחום במרחב. אבל אם מדעתי קודם כל את התדרים הנמוכים, כל התדרים הגבוהים, פשוט ברלקסציה שקראת שאני מבין, יכול להיות שהרזולוציה שלי למדוד את התדרים האלה השתנתה.
כן, אבל אם החומר שלי היה לו נניח T2 נורא 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 ארוך, או T1 נורא נורא, כאילו שני נורא ארוכים, זה לא היה משנה לי, כאילו זה היה רק טוב לזה.
כן, אם הוא היה נורא 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 קצר בקצה, יש לנו כאלה. יש לנו פרוטונים של פאט, לא רואים. הם פשוט, הם עושים דיפיידינג לפני שאנחנו מדבר על מדידה. אין שם אף אחד איתה. אז סתם לא רואים.
אז אין פה ממש, אין פה את המשחק הזה של כאילו ספין אקו שוב ושוב ושוב, וכאילו של לסובב את הכל
אפשר לעשות את זה, שים את זה, ועושים כל פעם תמונה בעוד תמונה, ומה שיקרה זה תתחיל לראות את האפקטים של הדעיכה של הטיפות, שכאן מולטיפל ספין אקו.
כן.
אבל בכל אחד מהם אתה תעשה את הפול קייס ספייס, ועוד הפול קייס ספייס.
כן.
כן. אנחנו מתעלמים מזה שיש דעיכה בתוך המדידה של קייס ספייס. אבל זה נכון שיכול להיות אם זה היה מה שמצחיק אותך, כל זה מצחיק פרגים של ה-case space acquisition, כי חשוב לך לראות יותר תדרים מסוג אחד. או אתה יכול להגיד, יש לי הרבה יותר סיגנל בתדרים הנמוכים מאשר בגבוהים, אז כדאי שאני אתאמץ להגיע לתדרים הגבוהים בתדרים הנמוכים בזמן. בסדר, כי המין הוא כאן מבטא, לא נורא שיקר, אבל לא שיקר.
באמת שעשית את השתי תמונות, אחת של התמונה של המראי ואחת של החב הזה, נכון? של התדרים? של המדיד? מה קורה בזה?
רגע, אני חייב לצור שחזור עליי, אם לא הייתי פה שעה שעה.
כן.
לעמוד כבר. לכם בזמן? אוקיי. Okay, so now when we have some kind of intuition, maybe about how images are being created, we can now start to do brain imaging. And we're going to look in this class about anatomy and how how these images are used to look at mostly about variation between individuals. That's the main thing that it's been used in neuroscience. So what I want you to remember that we talked before about these quantitative images, right? We can say maybe if we get an images and we do, let's say, in different inversion and so on, so we do whatever we did, but in different inversion, we are able to measure the T1, the time relaxation, right, and its position. And there are different sources of signal, T1, T2, magnetization transfer, which I will define later, proton density, which is the fraction of water to non-water. And so what people typically do, they're taking an image which is called a weighted image, which means it's an image that looks like a T1. It's weighted by the T1 effect, but it's not exactly a T1 map, right? So you can think about it as a soup, right? There's all these ingredients. Maybe one of them is more pronounced than the other, and the other one is like a bento box, which you actually measure specifically and getting the T1 values of this location, okay, of each position in space, and then you have units and so on. So most of the work currently is happening in here. In our lab, for instance, we try to push this, and there's others, of course, who try to do that. But we're going to start with this, with images. And so when we work with images, empty, unit, other units, fine. So what but I really want to cover, I don't know how I'm going to do that. These first things about, given that we have imaging, we need to think, I want you to be aware about image processing schemes and assumptions. So when you would look on article with images on them, that was using MRI. There was a full scheme of image processing underlying it, and I want to try to expose it for you and with you, so you would have intuition when you do that. Then a little bit of how things are being quantified using the non-quantitative images. There's still ways to quantify and compare between individuals. And last, a teeny bit about quantitative imaging. Not everything not going to happen today. Yeah. Okay. So back, qualitative images. This T1 weighted, for instance. There is a single equation. We didn't develop it, so I'm just telling you that it's possible to identify the single equation of the image, and we can take a specific alpha, which is a flip angle, and a specific TE, a specific TR. This is all parameter of the magnet, and we're going to get a weight of T1 and H, which is proton density, and T2 star in this case, and we're going to get an image. That will be a weighted image. Remember that, okay? So giving the parameter that we're going to use in the magnet, we're going to get an image. And we can vary them. We can vary the TE, start to get more and more T2 star effect, change the T1, that's going to change the flip angle, that will change the T1 weighting. Just I'm saying the same thing I said about the equation in images. You don't need to do the transformation now in your head. Okay?
What does it tell you that which signal where?
This is solving something called the block equation in steady state, because this is sequence. We cannot go into all of that. We can solve the single equation. What would the expected signal, giving the fraction of protons, how many protons there are in this voxel, what is their T1 relaxation, what is their T2 star relaxation, giving a specific TE, giving a specific echo time, giving a specific TR, which is repetition time, giving a specific flip angle. So different aspects of how we do the measurement and the underlying parameter of the tissue, how many protons there are there, and what kind of relaxation they got. That's what gives us an image in the end, a value in each location. Sorry.
Is it a function of time or space? What do you, I mean, is it a signal in specific space, specific time?
This is maybe my brain today. Okay, that's what you mean? If you measure it in more...
No, S itself.
So, okay, that's a good question. If T1 changing all the time in the brain, that's what you're asking? If T2 start changing all the time in the brain?
No, I mean, like, there are different signals in different times and in different areas.
Okay, so the underlying assumption is that we have water and non-water surrounding them, and they're kind of not changing too much. They're always changing, but they're not changing enough to make a difference on our signal. Okay, so we kind of like a constant thing. So now in 5 minutes, probably also in a year, roughly the same. We say we're going to talk about when not. And then if I will measure a measurement that kind of like cancel all this effect, I'm going to get only the proton density effect. So only something that will measure the amount of water, will be reflecting the amount of water at least. So if there is more water in the gray matter than the white matter, we'll see a contrast between the gray matter and white matter. And if there is a difference in T1 relaxation between the protons in the white matter versus the one in the gray matter, I will see that also in the image, right? And that's what we see in here. The white matter have faster relaxation, so they have a shorter T1 than gray matter. And in the ventricle, on the other hand, relaxation is very long. So that's weighting the effect of this T1. Okay? So giving the image parameters, I'm getting an image. Giving the specific TE, TR, I'm getting something that now in this case is weighted by the T1. Yes. So if the signal is arbitrary units. If I wanted to make it, so that make it an image. If I want to make it a map, I need to actually control it, maybe very flipping it in some controlled way, or maybe very TR or TE. And by that, I'm going to get sensitive to, let's say, T2 star or T1 or proton density and so on. So if I want to get a quantitative map with units, that's what was the bento box. That means that I would have to measure these things more than once and then fit a model, the single equation. Okay, but with weighted image, that's what most people do. And we have this contrast between gray matter and white matter, for instance, just because they have a different T1 relaxation and different amount of water. And that's become very, very useful. I'm going to show you how. So first, I want to tell you something about, let's say I measure the same subject twice, and I need to, so many times when you have images, there is some things we're doing with images. For instance, we might register them. What does it mean, registration? We might measure the same subject twice. This is coming from Shai's article, actually. And she measured the same subject twice, one with T1 and the other one was T2 weighted, never mind. And so she need to register them. It was the same brain, but it was measured twice, so she need to put them in the same common space. So in many cases we're doing that, and so we need to calculate where we need to shift this image, shift it in space, and then interpolate to get from these discrete values in each location the values in the new space. So that's called. So this is applying the transformation. We're gonna do some kind of interpolation between the position A and position A plus something to get the values in a position in the middle. Okay? So we're gonna calculate the transformation. I'm gonna show it to you in a few more slides, and then we're gonna calculate the value that we expect in a location which we never measured, somewhere between, let's say, two voxels. Okay. So to do this calculation, we can think about, there is a term called rigid body transformation. That means that we're only going to move this image or rotate it in space, but going to move it as a whole, okay? And so that gives us 6 parameters, 3 for transformation and 3 for rotation. And we can describe them in this matrix, which describes the transformation, how much we need to move them, and how much we need to pitch and roll and yaw of those images. Okay, so how much we need to move it. And then we can also add stretching. So it's still linear, but it's called affine transformation now. We might just stretch the image. Okay? But it's one stretch. It won't have the same effect everywhere, but it's one type of stretch. And so that gives us another 3 parameters. And then sometime we're gonna, let's say I wanna look on my brain and on Shai's brain in the same time. So I need to bring us both to some common space. So I might use something called warping. I'm gonna really squeeze the image, and let's say I'm gonna take this car and make it to be this car somehow. I need to like pull and push and pull and push. It's gonna be very local pushing and pulling until those two things will look the same. Okay? So many times people do that. That's called nonlinear registration of transformations. Okay? That have many more parameters. Okay? And whenever you do that, it's in the end a minimization problem. You say, I want to go from here to here. If you do it with rigid body, you use only 6 parameters. If you use affine, you use 12 parameters. If you have nonlinear transformation, you use many parameters. And whenever you fit parameters, there's always a risk of overfitting. Okay, so you have to remember that when you see work with imaging.
But in order to compare different...
Let's see what is done. Yes, you're using that. Yes, but then you have to be worried always. Some people forget to be worried. You don't have to do it always, but that's typically what is done. In here, in this case, Shai was using nonlinear transformation, and she was really worried, so she checked when it actually works and when it's not. Fine. That's what the reviewer asked her about that, how you actually make sure that your registration is fine. One image was actually a measurement which have EPI artifacts. This like we measure very fast case spreads, and the other one it was slower. And so there are different artifacts, and she had to use warping in order to get one image to the other. So the reviewer was asking, are you actually sure that they're in the same space?
How do you tell that this is good and this is
There was in here there are 2 images, and you can 1 second, and it look to you in the same by eye. You can actually calculate that. And in here you can actually see there is some kind of like motion. The registration wasn't really successful. Because what we're doing is we're fitting some kind of a minimization problem to find the parameter that transfer one to the other, whatever the problem is. And there is local minima, and there is noise, and sometimes we don't have enough parameter to fit it, and sometimes we overfit. There's many reasons why sometimes it does work and sometimes it doesn't. Okay? Please.
If I want to know how to align the two pictures, I need to decide which one should be actually the same so that I can even know.
So this kind of like, if they don't agree how we quantify that, I will do in a second. But you might think that you want to move them all to some common space and do your analysis. I'm going to talk about it a lot in a few slides. And you're right, you might say, but why would you do that ever? My brain and your brain is different, and there is no reason to put them in a common space and then do some analysis, because it might not be the same location, right? That's what you kind of said, I think. Maybe not. You want to ask again? Okay, so in the same brain, let's say I just measure the same subject twice, many times. fMRI, in fMRI we're doing that. And he might move. He moves. We always move in our scanner. We're breathing. By that we move. So I need to register 2 images. And I might say, I don't think there is any kind of like crazy affine. The measure wasn't stretched, and I was sampling case space the same, so I don't expect any kind of like manipulation. Just move. So I have one image, and have some kind of gray level in each location. I have another image, which have almost the same gray level values, but it's shifted in space. Okay, so now I'm going to write a minimization problem, which when I do one minus the other, I'm going to get the minimum value, okay, in each position. So I'm going to look for the 6 parameters that give me motion, translation, and rotation that will minimize the difference between the 2 images. So that's my minimization problem. That was rigid body. But let's say the case space measurement was different and there was some stretching. Maybe I will allow also stretch, things like that. Maybe it's totally different way. I really need to do warping. I need to like mush the images to get them to be together. More parameters. Okay. Now we're getting more to the next thing we can do with that. with these images, we can do segmentation. We can, given that there is different intensities, right? There is things which we have whiter values and darker or different gray levels, whiter region, gray regions, black regions. We have a distribution of values. We can try to segment everything which has a specific value. I'm going to assign it to a specific cluster. Let's say I'm going to call it gray matter, and the other one I'm going to call white matter, and so on. Okay, so segmentation is actually critical, and it's going to be very useful. Yes?
Segmentation of the signal itself to show it, or?
Yeah, it's going to be very useful for our analysis, but many times, when working on anatomy, segmentation is the initial step of our analysis. And some people will do it automatically. They take the grayscale values and just put a line somewhere in here, and going to get like 2 peaks. I assume 1 peak is gray, 1 peak is white. Well, others say, no. You have to do it manually. You go and draw, and so on and so on. Or maybe you put some rules in the way you do segmentation. You have some priors and so on.
This is for the study fixed white and gray matter, or the same thing?
In here, I'm defining it as gray and white matter. It's actually important what you just said. In the end, what we're doing, we're looking on the fact that there is contrast, and I'm just separating region with one level of gray values to other values. Other region would have a different gray level values. And I hope, in my mind, that this goes with gray matter, white matter, CSF. Some people forget that. They just hope. But also, if I have a lower contrast, that will be worse. It will be just harder. The peak's gonna get closer. Okay, so we are really sensitive to the SNR, to the weighting. All those things will make a difference. Okay, and then there are many tools to go and look on those segmentation in the different planes, to maybe edit them manually, to do some editing, maybe to look on that then in 3D, creating meshes. I'm going to show you that in a second. So that's become a huge industry that's supporting MRI. Most of the people coming from CS. So you remember I showed you this babushka kind of image of these people from different fields. So all this image processing from people coming from computational science, and we're getting many tools from them of image processing and so on. Okay, segmentation. Yes?
You do the segmentation based on, each voxel gets its density and then we divide the voxels? Or?
Each voxel gets a different density, but I need a contrast, right?
Yeah, but the contrast is within the voxel?
No. Between voxels. Each voxel have a single contrast. And so after I segment maybe to gray and white matter, I can take this gray matter, make sure that there is no holes and there is no, there's many issues in this. I actually need to make sure that it's actually continuous and so on. And then I can take these vertexes and maybe blow the brain, right? I can look at that in a balloon. I can blow it, right? I have a surface view, and I can play with this surface. Okay, that's very, very useful for fMRI, but for other things as well. Sometimes you see image. Here you see image like that. Here it is, right? This is a surface image when they project fMRI result on it. So that's how it's been done.
But this is 2D that you make.
3D. So given that you have a 3D image, many slices, all of them you have a gray-white matter borders. You make sure that they're continuous. If there is problem, you either automatically or manually fix it. And then you have the position of this vertex. I will show it more soon. So you have now some kind of if you want a balloon that is like a fold, and you can blow the balloon and fold it and so on. That's what you have in here.
I'm asking because it's like each slide is 2D and then.
No, so first those images typically are done in 3D. So we do 3D case-space measurements. And even if you do it in 2D, you just stack. You take slice by slice. You just take slice after slice, and so you assume they're continuous. And for this kind of analysis, you just assume 3D, because you have that slice and another slice. You need to make sure that there is no change in intensity between slices. There is issues with that, but yes, in here we assume already. Maybe you can stack these slices, so it's a 3D thing. Okay, so now there will be analysis on the surfaces on those images, and they will respect this image in a different way. So if remember we don't measuring in the units of the brain, right? Like in terms of we don't measure along those surfaces. We're just measuring in some grid. We have a value per voxel, some grid of these images, right? So those intensity in here coming from different voxels. So it could be that these 2 points, which are very close in image space, could be very far in brain space or in cortical space. Yes, you see that? That was clear? Right, they are really far. They might be centimeter apart, but in image space they might be millimeter apart. Okay, so why I'm talking about that? What are the things that we're typically doing with images, or with anything, actually with data?
We would lose data.
Yes, but what are we doing for SNR sometimes?
For what?
For SNR purposes, we sometimes smooth. So smoothing essentially just you take several measurements. So if you smooth in image space and it doesn't respect the coordinate of the brain, that will make it one kind of measurement, versus if you smooth along the surface, it will be a different kind. So you can smooth along the surface, just you need to first calculate the surface. That will make it totally different observation of the brain, right? So when you hear about the talks about fMRI, I don't know if they will talk about it. Typically won't. But you should remember, you can always ask, how did you smooth, in image space or in cortical space? That will change the essential resolution of your measurement. Okay, so that's exactly that. One type of smoothing, a different kind of coordinate, and then a different kind of smoothing. These points now are really far away from each other, and before they were under the same kernel of smoothing. Okay, so sometimes we see this kind of images in fMRI. Something is projected to the outside of the, not like in here when we actually respect the folding. In here, something was just projected outside. What does it mean? It means that there was some kind of experiment. There was a difference, and then they find it somewhere along this line, and they just project it outside to the image. So when things are just projected to the cortex, and that's sometimes you see that in works when you're reading work in MRI, you just should be appreciate that it can come from many locations. Okay, so this projection is kind of like you should be worried at least, or should be aware of what you think. So here is an example of activation in fMRI that was projected to the cortex using this approach, and that was for area which is activated with language, with words. Okay, and you can see that it's actually not in the same location each time, and it's like you might have a full theory about that, and you might say just because it's been done on this using this projection, while the area of activation, this VWFA area, which is activated with words, is really tiny. And it have other areas which creating different activation, and to be able to say something about the location and its interaction with the things near it and so on, you really need at least to work in this surface space to actually identify the small location of activation. Okay, so what I'm trying to say that the method of an analysis, I'm making this long story about images just to say that actually it will change totally the effective resolution that you are able to describe your data with. Okay, so in here you actually keep the resolution of the measurement, that is in millimeter. In here the resolution is actually centimeters.
So what's the point of projecting the information?
It's making beautiful images for journals. But you're gonna read articles soon, and they will have that, and you can have some kind of at least be critical about what you're showing. Okay, so there is some activation somewhere in this gyrus, or it's in this position and it's in this angle to the other activation. So something you can say it, and sometimes you can't, depend on the method that's been used. Okay. So what else we can do? So we're done with that. Now let's try to quantify things, giving this image and the segmentation of this image. And so we can quantify volume. We can maybe quantify morphometry. We're going to say what is morphometry exactly. or maybe you can quantify also cortical thickness. So that's the things we can, although the image were qualitative images, we can do quantitative inference about them, compare between group of subjects, given that we're doing the same pipeline to all of them. Okay? So for instance, I can, let's say in here, I segment the occipital lobe. Right? And the gray matter or the volume of this area, I can compare it between subject and say how that changed. It's function of age and function of whatever I want to measure. So, or maybe I can say something about how it shapes, how it looks. That will be morphometry, okay? Or maybe I can say something about the distance between the gray and white matter, the thickness. Yes?
Can you tell something about the density of it?
They call it density. That will be important to realize it's not density.
What?
You will see. The terminology density is used many times, but it's actually wrong. Yes, you cannot, unless you do quantitative imaging, you cannot say anything about the density. You can talk about the density of... No, you can't. You will see what they call density. Okay, so maybe you heard about this work. That's kind of one of the famous work, this one. With the taxi drivers in London. And their hippocampus was different. Maguire work. No? Okay, that was like kind of like... This work was... After they invent a method called VBM, I will describe it in a second. And so now I'm talking about... We're now moving to people with somewhere between image processing and statistics. Now, statistics become really important. So here is they were looking on the hippocampus. I will explain exactly what. I just want to show you like things that are done with this type of method, looking on those images. They identify the hippocampus, or no, they didn't identify it. They find that if they compare normal driver versus driver in London before Waze and GPS and so on, so they actually had to know the map. Okay, and then they found there is a difference in the morphometry, which we're going to define something about the volume or the structure in a particular location, which was hippocampus. So they felt that that's a measure that can say something about the quality or something that we learned and was affecting a specific area in the brain, the hippocampus. Okay, that's an exciting measurement that we can do something like that in humans. Okay, and I'm just giving you teasers or examples of. In here there was measuring longitudinally subjects and measure each portion of the brain and measure how it changes function of age. And they would notice that there are areas which have there is a strong effect of aging, other which doesn't, and that might be important. Okay, so this kind of analysis are also possible with the tools that we showed before. In here I took like the one which is the most complicated, just to show you where it can go. You can do this in the end going to be a network analysis. Okay, but you can define cortical layers, then say you can say what is the cortical thickness in each location. I'm going to explain each word I'm saying here in more details. But let's say we have cortical thickness in many locations, and then we can look on the variation. If one cortical thickness in one location can predict the cortical thickness in another location across subject, and if it does, they will assume they're varying together, and so they will do a network analysis. Let's say which area is varying together in terms of cortical thickness, for instance. Okay, so that's different kind of analysis you can do with this type of data or images. Okay. So now we're going to get to the details. What is VBM? That's the first method I want to discuss, called voxel-based morphometry. And that should get us some kind of a measurement of gross change in structure between subjects. Okay? And the reason that people like it is that they don't need to say where they want to measure. They're just taking one measure of T1 weighted. They do it on the group of subjects, let's say group A and group B. They don't know where it should be different. They will run this VBM. We're going to see what it means. And then they will do some statistical testing, and they will get the area which show the biggest difference, some significant difference, which we see how they identify significance, okay? So, and that's something that is widely used in MRI, okay? So this kind of measurement of gross anatomical changes between groups. And so the pipeline goes like that. Now you're kind of professional in all those steps. There is an image, there is a template in some common space. There is first normalization, which means registration, the nonlinear registration. So the registers all the way to the same common space. Okay? That's the first thing to do. Moving the image, the specific, my brain to this template space, and your brain, and so on. And then the next step is they have some parameters. Where is gray matter? Where is white matter? Where is CSF? There is also the intensity of the image. Using both, they segment, okay, and they smooth. So now we have a gray matter. We have the position could be gray matter, and after smoothing also could be like not exactly gray. So we have like different levels of grayness, okay, of a position. And we can do it in my brain, in your brain, and we're all in the same template, in the same space. So we can actually do it now analysis to ask how gray my brain versus your brain. And they call it density, by the way, the density of the signal, but it's not exactly density, okay? It's something to do with their ability to register, segment, the actually signal in there. Okay? So that's what VBM is doing. Normalization, we talked about that. This is just an images of the morphing. So how much we had to change. So this gives you actually a map of how much a position had to be like stretched. It's like a stretching map. Okay. Some people doing their analysis only on the stretching. When this thing is done, it's called the deformation-based morphometry, DBM. So that's if you only want to measure the amount of stretching, not the amount of grayness. That's also allowed. Some people do that. And then we have two groups. Let's say one of them have Alzheimer, the other doesn't. They are control. So we can look in each position and create this linear model that say, how can I explain the intensity in this location, given that this group is, I know they are Alzheimer disease patient versus not. And if I have a region which the beta values is really different, how much I can explain by the fact they are in one group versus the other, then I can say this area is significantly different between the groups. Okay, so that's the. Say it again. Beta is exactly so. I wanna explain the intensity in a specific voxels as function of if I was from this group, so if this is one or this is one, so I have two betas, right? It could be any, that doesn't have to be one. And maybe I have other things that I need to take into account, age and gender, and I don't know the size of the whole brain. So I'm taking into account all of those things and try to see if the intensity of this voxel is really different between this group versus the other group and can be explained by these betas, then I can say these groups are different in this position. So it is rather simple.
But if you check many parameters,
multiple comparison, you're asking, yes. So you do million correction for multiple comparisons, and there is a full literature about that. And some would say that this is still not a good way to check it. So what they would say, if you find something after this correction, it's really, really significant. It's huge. But yes, people are aware of that. It's true. So if I do so many comparisons, the first thing you should say, you have like thousands of comparisons, thousands of voxels. By definition, if you use, let's say, a criteria of 0.005, 5% would just pop, just because, right? And so we were doing multi-comparison correction is done in here. Okay. But what do we measure? It's called density sometimes. You will find it, people will call it density. Remember, it's not exactly density. It's something that has to do with everything. Also with density of tissue. Also with gross difference in volume, in the ability to segment, in the ability to register. All of those things will play along in our ability to say that area I have is different between the two groups. Okay, so in terms of specificity, it's not so great. Yes?
When someone doesn't know what they're just telling us, even less in a paper.
It might say gray meta density. So now you know. That's
But
the reason we have this class is that you would know.
Yeah, but, I mean, so is there another word for that? I mean, maybe they call density because they mix or.
I think if you read the original article by Ashburner and Flintstone, that the two people who invent this method, they would say we can do now statistical inference between the two groups. Let's call it this difference in intensity, density of the signal. So this, and we do it in the gray method. So let's call it gray meta density. Remember, this is not the real gray meta density, and nobody remember this. So from there on, it's called gray meta density.
And are these images?
But now you know.
Is it weighted by any parameter?
What do you mean?
Maybe I don't understand the signal they start with.
There was segmentation, normalization, segmentation, smoothing. There was a value then of how much grayish it was, if you want. And they compared the amount of grayness in my brain, in your brain. Or maybe in my brain, in this case, there was the people who learned to do juggling. So the level of grayness in the same subject is function of time.
Yeah, but what,
I don't know what it is. They actually don't care. Something about the way they run this pipeline. I'm not a great advocate for them.
Yeah, I know, but
I'm not trying to. I want you to be critical. I actually believe them that there is a difference here when you learn to do juggling. That's what I can say. What does it mean? I really don't know what it means. It's actually interesting. There is plasticity. That's what it means. Something changing in a subject that learned, in adults who learn to do juggling. That's exciting and interesting. And probably people replicate that, so it's you want to see replication on all of those things actually. But still, what does it mean? That's open for others to do then more research. Yes.
If you was first place T1 weighted or T2 weighted,
So it's also affecting by the fact that I use T1 weighted image for sure. Maybe if I would use a different image and do my segmentation, and I would show an article that criticizes that will change. Yes, giving the image that we use and giving the assumption that my T1 weighted and your T1 weighted was also the same. If there was a little bit difference in the way my image came out in terms of weighting of T1, that could be the main source of the difference. Yes?
you're saying there's a difference, but you don't know what it means. So what does it tell you?
For instance, in here it means that there is a difference in this position or around this position, some grossly around this position, by learning to do juggling. Or maybe it was about Alzheimer. You may say there is some difference in the hippocampus that you couldn't maybe tell before, or that it exists. Or you can say that the effect is changing as the progression of the disease, and there is a critical period of progression, and so on. You can say many things. You cannot be very specific of what it is. Also, not exactly where it is. Kind of bulky where it is. It's more than nothing. You're joking, but how would you say that otherwise in humans? It's really hard, right? There is a reason this method exists, because there is no other way to do that. And let's say I want to learn something about the variation between individuals. It's actually hard. Time, huh? Fine. Time. Yeah, I'm not going to start this one. Next is going to be cortical layers, and then I'm just going to say what's going to be in the next class.
Next week there is Purim.
Next week there is Purim. Good for us. In 2 weeks. We're going to look about the analysis that can be done along the cortex. Okay? Which is kind of the same same flavors, but maybe more specific because you're looking on those cortical thickness, whatever it's measured. And then we're going to say something about try to quantify those T1s exactly with units. And then I'm going to move to another measure called diffusion, and other things we can measure about brain structure. Okay? Thank you.